Find the vector product of vector p and vector q. So here we want to take p and cross it with q. So the first vector crossed with the second vector. So the order is important. So presumably we're doing it in this order, in the order in which the vectors appear, because if we do it the other way we get a different answer. So as we saw in the previous video, we get the determinant of the following matrix. The first row consists of unit vectors I, j and k. The second row is the components of vector p. So the I component is -2, the j component is -3, the k component, as you can see, is 0. There's no k component for vector p. The I component of vector q is 4, the j component is 7, the k component is 0. Okay, we start with I. That's assigned a positive sign. The upper left entry of any matrix is assigned a positive sign when we take its determinant. So we can put a plus in here if we like. Next we get the determinant of the 2 by 2 matrix that remains when we cross off the row and column that I is on. So we want the determinant of this matrix here, -3, 0, 7, 0. Next we go to j. That's assigned a minus sign, so we follow the checkerboard pattern now. If one entry is a plus sign, then the entry next to it, to the right of it, or indeed below it, has a minus sign. So we're just working with this row. So we minus j, and we have to get the determinant of the matrix that remains after we cross off the row and column that j is on. So it's -2, 0, 4, 0. Finally we have this entry here, which is plus. These entries alternate, just like the black and white squares on a checkerboard pattern. So we have plus k, and we get the determinant of the matrix that results when we cross off the row and column that k is on. So we have this determinant here. Okay, if a row or column of a matrix consists entirely of zeros, then its determinant is 0, because -3 by 0, as you can see, -0 by 7 will give us 0. Simple to see for 2 by 2 matrix, and it's true in general for any matrix actually. So we're going to get 0 I here, we're going to get a 0 j here. Now over here we have k times -2 by 7 is -14, minus -3 by 4. So we multiply these entries together, then we have a minus sign, and we multiply these entries together to get -12. So we get -14 plus 12, so we end up at -2k. Notice that these are two vectors in the xy plane. The cross product of them is a vector that's perpendicular to both of them. A vector that's perpendicular to two vectors that are in the ij plane must be a vector along the z-axis. It's actually along the negative z-axis in this case. Here we are given the coordinates of the 3 points A, B and C. We want to find the vector product AB cross AC. So here's a rough sketch of them. I've made no attempt to plot them exactly, of course. These are points in 3 dimensions. Let's start by getting vector AB. So we have to take the coordinates of the head of vector AB, which is the point B, and subtract the coordinates of the tail of the vector AB, which is the point A. So we have 3 minus 9 is -6i. Then we have 1 minus 1, that's 0j. Then we have 3 minus -2, that's 5k. AC is the vector whose tail is at A and whose head is at C. So we take the coordinates of the head of the vector and subtract the coordinates of the tail. So 1 minus 9 is -8. 0 minus 1 is -1. That's -1j. Then we have -1 minus -2. That's plus 1k. Now to get AB cross AC, we get the determinant of this matrix. The first row, as we've seen before, is ijk. The second row is the components of vector AB. The third row involves the components of vector AC. So we take I, it's assigned a plus sign as we know, and multiply by the determinant of this matrix here. So we cross off the row and column that I is on, and we're left with this matrix 0, 5, -1, 1. Then we have minus vector j, following the checkerboard pattern, and we multiply that by the determinant of what's left when we cross out this row and column that j is on. So it's -6, 5, -8, 1. finally we have vector k. It's assigned a plus sign, of course. Cross off the row and column that k is on. Take the determinant of the remaining matrix. So we multiply 0 by 1 to get 0. Then we have a minus sign. 5 times minus 1. Minus plus 5 by minus 1. That's plus 5. Here we have minus 6 by 1. Minus 5 by minus 8. That's minus 6 minus 40. It's minus 46. Actually, it's minus 6 minus minus 40. That's minus 6 plus 40, which is plus 34. And here we have plus 6 minus 0. So we get 5i minus 34j plus 6k. So this vector is perpendicular to both of these vectors. So it's actually pointing down like this, into the screen if you like. If these two vectors are in the plane of the screen, then the cross product will actually be into the screen. Now I used the arrow notation in previous videos. I use a dot to indicate something going into the screen, but I won't do that here. I'll just use perspective here. So AB cross AC is got by rotating AB towards AC about this point. So that's a clockwise rotation, so it's like we're closing a screw cap. So the screw cap is moving down as we close it on a bottle, clockwise to close. So this would be the direction of AB cross AC into the screen. So as I said already, it's perpendicular to both of these vectors, AB and AC. Finally, let's see that the associative condition for the vector product does not hold. Well, at least in general, it does not hold. So let's consider this example here, I cross j. In a previous video I explained that if we take the cross product of I with j, we get k. We just write I, j and k down like this. And if we take, say, two of them consecutive terms in this triple, I cross j will give you k. J cross k will cycle back to I. K cross I will give you j. It just cycles like that. So it's a quick way to take cross products of these unit vectors. So I cross j is just equal to k. So this is going to be I cross k. Now how do we get this? K is 2 steps ahead of I. Well, what we do is we consider k cross I. So I comes after k in this cycle. So we would say the term immediately after k is I. So k cross I gives us j. So we know what k cross I is. And if we know what k cross I is, we can get I cross k. We know that if we reverse the order of the cross product, we change the sign. So we change this from j to minus j. So this is equal to minus j. Alright, now let's consider moving the brackets of this triple. So let's bracket I cross I and cross the result with j. Are these equal? Well, I cross I is just 0 because the angle between these two vectors is 0. These are parallel vectors. The cross product of a vector with a vector parallel to it is 0. So we get 0 cross j. If we cross 0 with anything, we get 0. We could just go back to the basic definition of the cross product. Get the magnitude of 0 times the magnitude of j times the sine of the angle between them. Well, it doesn't make any sense actually for angles between these vectors. The result is just 0. So you see that the order in which we do the crossing, well, I mean, which pair we cross first does matter. It's not the order actually. We haven't changed the order of the i's and the j, but we have placed the brackets in different position. So if we do it this way, we get minus j. If we do it this other way, we get 0. So this single counter example is enough to show that the associative property does not hold for the cross product of vectors.